Keynote Jan Cami. So I would first like to thank all the people in leadership positions of Cosmic Nanospace and Abundant in Space, even though, and this sounds very good. So I just gave a presentation titled Future Directions in Cosmic Fullerenes. So the big picture of this is we are at a meeting about nanoparticles in space, carbonaceous nanoparticles in space, which is a really big field. There's a lot of stuff out there that we don't really know, that we don't fully understand. And it's a bit of a question like, how do we make like clear, measured and directed progress in that field? And so one of the things that I suggested is to use cosmic fullerenes for this. And so fullerenes are a subset of these nanoparticles. They're carbon cages, essentially. The most famous example is C60, Buckminster fullerene, or buckyballs, as they're called. And so I think if we really study this species very carefully, we can actually make a lot of progress, not just for that one species, but because the molecular properties of fullerenes and a lot of other of these nanomaterials are essentially the same. Understanding the molecular physics will actually help us to break open this entire field. And so we have seen C60 at infrared wavelengths in Spitzer observation of a variety of sources. So it turns out they're widespread. We see them in evolved stars, in young stars, in the diffuse interstellar medium. However, we don't frequently detect them, but when we detect them, it turns out they're actually abundant. You know, in some cases, abundance estimates are up to like 2 or 3% of the available carbon, which is enormous for a single species. And so it's a bit at odds with the fact that we only rarely actually detect these species. And so in addition, if we look at infrared emission, we think we have an understanding of how these molecules interact with their environment. They absorb a UV photon, and then they essentially emit that energy through infrared vibrational bands. And if we make a model for that, actually the predicted emission for C60 does not really correspond very well with the observations that we have. And if we use a different model where we assume that the emission is thermal, for instance, we also don't get a really good understanding or correspondence with the observations. So there's a few things that obviously we're still missing. And so if we take a little bit of a step back, I think there's 4 questions in particular that we need to focus on for C60 to study. And if we answer those 4 questions, we'll actually make a big step forward towards understanding many more of these materials. So the first question is, what is the inventory of fullerenes in space? So fullerenes are these carbon cages, but you can make them smaller than C60 or larger than C60. You can add stuff to them. You can add hydrogen to it or another carbon or metals. They will have their own spectral features as well, and they might actually be present to a certain degree in space as well. So people have looked at this, have studied this, but it's not entirely clear at this point how much they actually contribute to the emission that we observe and ascribe to C60, for instance. That's like a first question that we need to address. The second one, and I think this actually is the most important one to kind of further our understanding, is what makes them emit? What is the excitation mechanism? So as I mentioned, if we use fluorescence, it doesn't really work. If we use a thermal model, it also doesn't really work. So we need to kind of look at many more details in all these processes. What really plays a role in the molecular physics in these sort of environments, and can we figure all that out? How does the charge state play a role? How do certain chemical pathways play a role? How do specific processes that cool molecules, for instance, recurrent fluorescence, how do they play a role? Can we build one model for C60 that takes all these physical properties and processes into account, and can we use that to then predict what the infrared emission should be, and does that match the observations that we have? If we can do that, I mean, that's a really difficult task, but if we can do that, that actually will drive the field forward enormously. The third question is, how do you actually form DC60? There's like two big competing ways. One is the bottom-up formation mechanism, where you build C60 from putting smaller units together. The other is you start from something larger and you kind of break it down to smaller things and curl it up. So both have their merits and their shortcomings, and it's not entirely clear which of those actually is responsible for the C60 that we see in space, and it may be that different environments have their own growth processes, for instance. That's also something we need to figure out, and one way to do that is so in these laboratory experiments we have, for instance, taken large pAHs, irradiated them with UV photons, and you strip away the hydrogens, and then you curl it up and you make C60. So we know that that process works in the lab, but does it also work in space? And so somebody needs to model this and say, like, well, we have these measured parameters in the lab. Let's now simulate putting this molecule in this irradiation environment in space and see what happens. Is the same thing going to come out, or is this a process that works in the lab but not in space, for instance? Kind of important to know. And then the final point is related to the fact that we see high abundance of C60 when we detect it, but we don't see it very frequently. And to me, that indicates that something is happening to C60. For instance, if you focus on planetary nebulae, what you see is that you only see C60 in young, low excitation planetary nebulae. We don't see C60 in the more mature planetary nebulae, and the question is, like, why is that? Is C60 getting destroyed? Could be, but you actually need high energy to destroy C60, and so I don't think that's very likely. What I think is more likely is that you actually do things with C60. You can make chemical reactions and add stuff to it, and if you build other things on top of your C60 cage, you remove the spectroscopic signature of C60 from your observations, and you make other things. And so we haven't even scratched the surface of the processes that are responsible for that sort of removal of the C60 signature from the observations. So that's the four big questions, I think, for cosmic fullerenes. We'll need a lot of people to actually address all these questions. We'll need lots of astronomical observations, laboratory experiments, theoretical calculations, and lots of interdisciplinary discussions like we had at this meeting. And I strongly believe that we can actually figure this out, and we will figure this out. And once we have figured it out for C60, it's going to impact a lot of other fields as well. So I'm very optimistic about it.